Good evening, welcome. Today I'm going to review the class, the course on architecture and organization of the computer. So this review class is about the readiness exam, and the readiness exam will be tomorrow. So I wish you all good luck with the preparation. So I will start by first explaining the content, and then I'll go in details with the preparation. So it is number 2 in the list, and the weight will be 11%, and there will be 8 questions. So the topics will cover digital logic, digital systems, and the representation of data on the machine level. This has been covered by Mrs. Abir. And today I'm going to cover machine organization on the assembly level, and in addition to the architecture for memory system, interfacing, and communication. So I will start by describing the I will start describing, just let me hide this one. Okay, so now I'm done. So I will describe the difference between computer architecture and computer organization with some examples. So there are two terms that you will often encounter. So what we mean by computer architecture is attributes or the attributes of the system which are visible to the programmer. And those attributes have impact, so they can, in a way or another, have a direct impact on the way the program is executed. Okay, so the program will be affected by the computer architecture. For example, it can be the instruction set, or sometimes we refer to it as the instruction set architecture. The number of bits used to represent data types. For example, how many bits are represented how many bits are used to represent integer, how many bits are used to represent floating points, etc. The input-output, and techniques to access to the memory. So the addressing, the way the memory are addressed. So all of these are example of the computer architecture. So the programmer should know those attributes so that he or she can optimize the execution of the program. On the other hand, the computer organization is mostly deals with the hardware, things which are hidden to the programmer or to the user. Okay, so those will contain details of the hardware. For example, the control signals, the interface between the computer and the I/O, the memory technology, the type of the Ethernet card, etc. So the type of the screen. So all of these are hidden from the programmer. For example, you can consider the operation units, like the ALU, the different registers, etc. All of these are part of the computer organization. Okay, now things should be clear, the difference between computer architecture and computer organization. Now, when it comes to the types of the computers, there are 3 categories. The first one, which we all know, it is what we call the personal computer, the PC. So the PC should have a good performance for the single user. It should be affordable, which means that the cost should be in the range that an average person should buy it. And it should also support third-party software. So the user would like to install a third-party software for their own purpose. Now, the second category, we have the embedded computer. These are getting more and more popular because of the explosion in the IoT domain. So it is what we mean by the largest class of the computer. It should execute third-party software. It is usually designed to run only one application or some related application. It should have minimum performance because usually the embedded computer have low resources like RAM and CPU power. It should be low cost because it should be used everywhere. For example, in smartwatch, it could be used in your washing machines, in your cars, etc. So it should be low cost, and it should consume low power. Most of them should be low power because they are usually battery powered. Now, the other third category, the server. So the server should be accessed via a network. It can be, for example, a cloud server. It can be a fog server. It can be a data center. It should carry large workload, because there are millions of users will be accessing the server. Take, for example, the case of YouTube. So the YouTube from Google is a huge server, and the server holds millions of videos or billions of videos, and these videos will be accessed by people connected from all over the places. So this the workload should so the server should manage large volume of work. So that's why it should have a huge computing power, storage, and input-output capacity. And the server should be designed with the emphasis on dependability, because if the server is down, then millions of users will be affected, and this will also be costly in terms of revenue. So those are the three types of the computer. Now, if you look at the typical computer, so the typical computer will be composed of four main things. So inside you have the input-output. This is which is used by the computer to interact with the external environment. So you have the main memory, and later on I will detail the architecture of the memory and technologies, and the CPU. Now the CPU will be composed of register, arithmetic and logic unit, internal bus, and the control unit. So again, the control unit, which is a part of the CPU, will be composed of the sequential logic that will be used to organize the instruction one after the other. It should also contain control unit, register and decoder, and the control memory. So the control memory are used by the CPU to access to the main memory. And again, in the computer, all of this will be connected with the system bus. Inside the CPU, all of this will be connected by the internal bus. So the internal bus are wires which connect all these units. And the system bus are also wires, but should be off chip. Take, for example, the PCB, printed circuit board, and this should connect all these IOs, main memory, and the CPU. Now, when it comes to the performance, there are different ways to increase the performance when it comes to the computer architecture. So you can increase the performance by fine-tuning the algorithm, which means that we should make emphasis on optimizing the algorithm by reducing, for example, the computational load of the computer, of the algorithm, by having less and less memory storage. And this will determine both the number of source level statements and the number of IO operations. You can also increase the performance by having a good programming language, compiler, and architecture. So those will determine the number of computer instructions for each source level statement. The third way to improve the performance is by having a fast processor and also fast memory system. This will determine how the speed of executing the instruction. The last one will be the IO system, and this will determine how fast you will access the IO operations. For example, how fast you will be accessing the hard disk, how fast you will be collecting the data from the internet, how fast you will communicate with the mouse, with the screen, etc. So all of these will be affecting. So those are the software and hardware. So the algorithm will be the software, programming language, computer, and architecture are the software, because the architecture deals with the instruction set. However, the processor and memory are the hardware, and the IO system are composed both of hardware and software, because the operating system is also a complicated piece of software. Now, this is typical example from benchmarking. How will different categories will affect the performance. So if you use data level parallelism, you can improve the performance by 3.8. If you work with the instruction level parallelism, you can improve the performance by 2.3. Memory hierarchical optimization, that's I will emphasize later on. It has impact of 2.5 times. However, thread level parallelism will have impact of 14 times. So here, the best way to optimize the performance is to work with the parallel algorithm, and that's what we covered in the parallel and distributed system. So by having the algorithm to run in parallel, then you will improve the performance, and this can be reflected into Amdahl's law. Okay. So the 8 breakthroughs which improve the performance. So first of all, on the technology side, so the Moore's law predicted that the number of transistors will double every 18 to 24 months. This can be reflected into the improvement in the speed of the processor. The second factor, it is the abstraction layer, which has both simplified the design of the hardware and software part. I will see it later on, especially when it comes to the software. Faster common case. You do also parallel processing, pipelining, prediction when it comes to the pipelining, memory hierarchicals, and dependability using redundancy. So all of these have impacted the performance, or have improved the performance over the years on the processor. Now, when it comes to the abstraction layer, so this is typically what you have. So you have the lowest part, which is the hardware. So above that, you have the system software. Usually it is operating system, which will interface between the application and the hardware, and the operating system should manage the resources in a very efficient way. Okay, so without the effective software, system software, you'll not be using the hardware in a very optimal way. Okay, so in the above, you have the application software, for example, PowerPoint. It is usually written in high programming language like C++ or Python, etc. And then underneath, you have the system software. So the system software, it is typically the operating system. In addition, it has the compiler, which translates a high-level language into the machine code. So the operating system, which is a software that lies between the hardware and the software, it can manage the input-output, it manages the memory and the storage, it can also schedule tasks and share resources. So we have seen this in the review part of the operating system. So here, it's very important piece of software that makes the use of the hardware very, very efficient. So the lowest part, the hardware, which is the actual chips, it contains processor, memory, and I/O controllers. Now, when it comes onto the programming language, so those are the abstraction layer. So the lower part, you have the machine language, which is usually in binary. It is hard to read and interpret. Above that, you have the assembly language. Still, it is connected to the hardware, but it is less tedious compared to the machine language. And then you have above that the high-level language, like C, Fortran, and Pascal. And above them, you have the object-oriented and visual language. So if you work at this level, it is very, very fast to develop a code using object-oriented and visual language compared if you work with the assembly or the machine language. However, here you should rely on the tool that will translate whatever instruction you write in here into the machine language, so that the hardware will be able to execute and run your code. Now, this is a typical example. So this is the C program. So this is swapping. It will swap two values, VK and VK plus 1, using the temporary variable. You see, this is a very compact piece of code in C. If you compile it using MIPS, which is a type of the RISC processor developed by ARM. So this is the name of the function swap, and then you can see this is very much connected with the architecture of the instruction set architecture. So it is tied with the structure of the hardware. Okay, so here it is multiplication add. Here you will access the memory for loading, here for store, and here jump. Now, if the processor will not understand the statement, so it has to be translated into binary code, and this is done using the assembly. So the compiler will translate your C language into the assembly, and the assembler will translate your code into the machine code, and the processor will be able to execute this by accessing instruction by instruction and decoding its instruction and execute according to the way the instruction should be executed. Okay, now when it comes to the memory, there is usually a huge gap between CPU and the memory. So the references will start from 1980s. So in the 1980s, the performance of the CPU and the memory were equal. Okay, which means that if you improve the CPU, you should also improve the memory. So any improvement in the memory of CPU will have a big impact on the design of your system. However, if you look in here, so the CPU, the performance have increased because of the technology. However, the improvement of the memory didn't follow the way the performance of the CPU have been done. Okay, so this has created what we call a gap. So the gap between CPU and the memory. So to remedy this gap, there are techniques using memory hierarchical to reduce this gap, because most of the programs will need to access to the memory. So it's not enough to improve the performance of the CPU. We need also to improve the memory. However, with the technology, it's not possible. So we have to resort into another techniques. So the techniques which are used often, it is based on the locality. So if you write a program, there should be some temporary locality, which means there is a possibility that if you declare a variable and used in the beginning of the program, there should be also high probability that you will be using this variable later on, and this will create a temporary locality. In the same way, so most of the codes that you write, they are using arrays or vectors or matrix. So there is some special locality, which means that the data should be organized next to each other in addition to the instructions. So there is also a high possibility that if you access one data, you will need to access the data next to it. And this is what we call the special locality. So all of this should be used to improve the performance of the memory. Okay. So if you look at the memory, so you have three types of the memory hierarchical, and this will improve and reduce the gap between the performance of the CPU and the memory technology. So on the first level, you have the cache. So the cache is usually on the same die. So it is very close to the CPU and very fast. However, it's very expensive and consumes lots of area. We'll see later on what is the technology used to make up the cache. So of the chip, you have the main memory. This is the RAM, in which it will store your data and also the instruction. And so the data here are stored temporarily. So to store this data in a long term, we have to use the hard disk, and those are the three levels of the memory. So we have the cache, main memory, and the hard disk. Now, those are the memory hierarchical. So a typical processor will have a cache, and the cache are usually made up of the SRAM. So the SRAM is the main technology used to construct the cache. Think of it, this is like made up by the transistor, and the transistors are stacked together so that you form sequential logic, and the sequential logic are used to the cache. So typically, you can see it as a connection of different registers. So the registers are also type of caches. Now, the price is very, very, very high. So you can see that it is $100 per gigabyte. The access time is between 0 to 3 nanoseconds, and also has a high bandwidth. You cannot afford to have a huge SRAM, then you can resort into the main memory using DRAM. So the DRAM, in which one transistor will hold the data. So in a way, it will consume less area and also be less costly compared with the SRAM. However, you can see that on average, it is 30 times slower than the SRAM, and also the bandwidth. Now, the DRAM, it is also limited in size. So if you have a huge program and a huge data, you need to use what we call the virtual memory. So the virtual memory, there are two technology. Either you can use SSD or HDD, so hard disk drive or solid state drive. Now, the solid state drive is getting very, very popular, and it is made using the flash memory technology. So the price is about 0.10 US dollar per gigabyte. This is the access time is 20,000 nanoseconds. You can see that's very, very slow compared with the main memory and also compared with the cache. So that's why we need to be careful, or the program needs to be careful, so that it will not often access to the virtual memory, because this will slow down the performance of your system. And this is the bandwidth for SSD. However, if you have the choice between SSD and the HDD, and you don't have constraint with the price, then you should go for the SSD, because you can see that the SSD is much more faster compared with the hard disk. and you can see it if you buy a laptop with SSD. You can notice it's very fast compared with the hard disk. Now, when it comes to the access to the different level of the memory, usually the processor, the first thing, if it finds a load or store operation or memory operation, it will look for the data. For example, suppose that you'd like to load a variable inside your CPU. So the first thing, the processor will look for the data in the cache. If the data in the cache is there and updated, then it will copy from the cache, as it has to ask for the data from the next level. So here the data are usually copied from one level to the other, which means that if you have the data in the virtual memory and you would like to push this data towards the cache, you need first to copy the data from the virtual memory into the main memory and the main memory into the cache. The same goes if you'd like to update. Suppose that you have updated the variable based on some arithmetic operations, then the processor will update first in the cache, and then from the cache it will be updated into the main memory, and from the main memory it will be updated at the virtual memory. In total, you need to have what we call cache coherence. So the data should be updated everywhere. So it should be updated in the cache, in the main memory, and the virtual memory. And this is shown in the blue box. So here the data, it is a copy of the same data which is in the main memory. Now, if when it comes to the cache, there are different technologies, there are different terms that are used to describe the cache. Usually, the cache, they copy the data by blocks, which is also referred to as cache line. And it can be multiple words, and one word can be 32 bits. So if the processor accesses the data and the data is at the cache, then it will generate a hit. Else, it will have the miss. So if the data is not in the cache, then there should be a miss penalty, because you need to copy the data from the main memory into the cache. If the data is not in the main memory, then you also create another miss, and then you need to copy the data from the virtual memory into the main memory, into the RAM, and this will create also an additional penalties. Now, in total, if you have for the performance of the cache, so you need to compute the hit rate. So how many hits with respect to the memory access. So ideally, you would like to reach 100%, which is almost impossible to get it. But it should be more than 80%, so that the performance will be up. So 80% of the data or the instruction should be actually within the cache, and you should minimize the miss rate. So if you optimize for the hit rate, of course, the miss rate should be reduced. And you can see the impact of all of these parameters into the AMAT. So the AMAT, which is the average memory access time, so it is equal to the time to access to the cache plus the miss rate in the cache. So which means that if you have a miss rate, the data is not in the cache, then there is some penalty in which you will access the data from the main memory. Else, if the data is not in the main memory, then you need access from the virtual memory, because you have the miss rate in the main memory. So you should seek, or the cache replacement algorithm should seek to reduce the miss rate in the cache. So if you reduce the miss rate of the cache, then these terms will be small. Else, if you don't optimize this, then your average memory access time will be long, and this will impact the execution of your program. Now, the cache terms, you have first to define the cache by the capacity, which is usually the number of data bytes in the cache. You have also the block size. So the block size, which is denoted by B, which is the number of bytes that can be transferred from the cache at once. And then you have the number of blocks, which is B equal capital C divided by B. And the number of caches so the number of blocks, B, capital B, should be equal to the capacity C divided by B. You also have the degree of associativity, which is equal to N. So N will define the number of sets. So S, which is equal B divided by N. So in the first trivial way, you have what we call a directed mapping cache, in which the number of sets is equal B, which means N is equal 1. And here I'm taking a very simple example. So in this example, you have the memory. This is the main memory, and then you need to copy the data from the main memory into the cache. So the cache is of length 8 blocks. So you can see the blocks are numbered from 0 till 7. So in total, you have 8 blocks. And then the way you will copy the data from the memory into the block using this formula. So you have the block address modulo the number of blocks in the cache. Usually the number of blocks of the cache should be power of 2. For example, here it is 8, so 8 is equal 10 to the power 3. So if 8 is equal 10 to the power 3, then you can notice that if you'd like to move this data, the way to know to which block it will be copied, you just have to consider the 3 bits, because the size of the cache is 8, and 8 is equal 10 to the power 3. So 3 you will use the 3 lowest bit to determine to where the block, to where this data will be copied. For example, here so 11101 will be copied into the location 5. So this is 5, and you can see that because the size of the cache is small compared with the RAM, so there should be kind of conflict. So you will do mapping of several memory location to the same block. Okay, so if this is not carefully designed, then you will create a mess. I will explain later on with some typical examples. Okay, so to know so if you have a data here, the data can come from this part, can be from this part, but can be from this one, of this one. So these are the blue lines. So to know the difference between, or the physical address, you need to use what we call the tag. So here here is the so here is the complete address, memory physical address of the memory in which the data resides, and the lowest part will be used to seek the right block number. The other part in here are identified as a tag. So the tag will be used to physically access the memory, and then you will copy this into the block. So this will be the address of the block, and in total you have to use the tag plus address of the block to find the exact address of the variable in the memory. In addition, you also have the validity bit in the cache to say whether the bit has been updated, the data has been updated or not. If the data is not updated, then the validity bit will be 0, and then the processor has to update this from the main memory, or it has to update it from the virtual memory. So if the data is not updated, then you will have what we call a miss. So those are the type of misses which are generated by the cache. You have the compulsory miss. This is because usually the cache is not updated, so for sure you will have compulsory miss. You also have the capacity miss because of the size of the cache. So if the cache is full, then you need to replace, and this will create some conflict, some misses. You also have the conflict, in which the data might be mapped to the same location, and so if you have misses, you will have to pay a penalty, and the penalty will be the time needs to copy the data from the lower level in the hierarchical. Now the summary of the cache. So the cache will have a capacity C, a block size B, and the number of blocks, and also the number of sets, and the relation between all of them will be S is equal B, capital B divided by N. So this is a table summarizes the feature of the cache. So in the direct mapped cache, you have N is equal 1 and S is equal B. And the N-way set associative, usually N should be between 1 and B, and the number of sets will be B divided by N. This should be integer. And the fully associative, you have the S equal to 1, which means that N equals to B, and this is the extreme cases. Okay, so remember, if you increase the number of N, then you can reduce the conflict, so the miss because of the conflict, or the conflict misses. So those are the references for this today's review class. So Peterson and Inercy is called Computer Organization and Design using RISC-V, because this is a trend. So the trend is to use RISC-V. Initially, people used to teach using RISC technology, for example, the ARM or Raspberry Pi. Now they're moving into RISC-V, which is an open open instruction set architecture. Okay, and the second excellent book, which is by Harris, it is published 2022, is called Digital Design and Computer Architecture, the RISC-V edition. So I hope I have helped in summarizing the most essential stuff in the computer architecture, and I wish you good luck with your exam.